So a lot of the ways that we represent multivariable functions assume that you're fluent with understanding how to represent points in 3 dimensions, and also how to represent vectors in 3 dimensions. So I thought I'd make a little video here to spell out exactly how it is that we describe points and vectors in 3 dimensions. And before we do that, I think it'll be valuable if we start off by describing points and vectors in 2 dimensions. And I'm assuming if you're learning about multivariable calculus that a lot of you have already learned about this, and you might be saying, what's the point? I already know how to represent points and vectors in 2 dimensions. But there's a huge value in analogy here, because as soon as you start to compare 2 dimensions and 3 dimensions, you start to see patterns for how it could extend to other dimensions that you can't necessarily visualize, or when it might be useful to think about one dimension versus another. So in 2 dimensions, if you have some kind of point, just, off sitting there, we typically represent it. You've got an x-axis and a y-axis that are perpendicular to each other, and we represent this number with we represent this point with a pair of numbers. So in this case, I don't know, it might be something like 1, 3, and what that would represent is it's saying that you have to move a distance of 1 along the x-axis, and then a distance of 3 up along the y-axis. So, this, let's say that's the distance of 1, that's the distance of 3. It might not be exactly that the way I drew it, but let's say that those are the coordinates. What this means is every point in 2-dimensional space can be given a pair of numbers like this, and you think of them as instructions where it's kind of telling you how far to walk in one way, how far to walk in another. But you can also think of the reverse, right? Every time that you have a pair of things, you know that you should be thinking 2-dimensionally. And that's actually a surprisingly powerful idea that I don't think I appreciated for a long time, how there's this back and forth between pairs of numbers and points in space, and it lets you visualize things you didn't think you could visualize, or lets you understand things that are inherently visual just by kind of going back and forth. And in 3 dimensions, there's a similar dichotomy, but between triplets of points and points in 3-dimensional space. So let me just plop down a point in 3-dimensional space here. And it's hard to get a feel for exactly where it is until you move things around. This is one thing that makes 3 dimensions hard, is you can't really draw it without moving it around or showing a difference in perspective in various ways. But we describe points like this, again with a set of coordinates, but this time it's a triplet. And this particular point, I happen to know, is 1, 2, 5. And what those numbers are telling you is how far to move parallel to each axis. So just like with 2 dimensions, we have an x-axis and a y-axis, but now there's a third axis that's perpendicular to both of them and moves us into that third dimension, the z-axis. And the first number in our coordinate is going to tell us how far, can't move those guys, how far we need to move in the x direction as our first step. The second number, 2 in this case, tells us how far we have to move parallel to the y-axis for our second step. And then the third number tells us how far up we have to go to get to that point. And you can do this for any point in 3-dimensional space, right? Any point that you have, you can give the instructions for how to move along the x, and then how to move parallel to the y, and how to move parallel to the z to get to that point, which means there's this back and forth between triplets of numbers and points in 3D. So whenever you come across a triplet of things, and you'll see this in the next video when we start talking about 3-dimensional graphs, you'll know, just by virtue of the fact that it's a triplet, yes, I should be thinking in 3 dimensions somehow. Just in the same way that whenever you have pairs, you should be thinking, this is a very 2-dimensional thing. So there's another context, though, where pairs of numbers come up. And that would be vectors. So a vector you might represent, you typically represent it with an arrow. Whoa. Help, help. So vectors we typically represent with some kind of arrow. Let's this arrow a nice color. An arrow. And if it's a vector from the origin to a simple point, the coordinates of that vector are just the same as those of the point. And the convention is to write those coordinates in a column. It's not set in stone, but typically if you see numbers in a column, you should be thinking about it as a vector, some kind of arrow. And if it's a pair with parentheses around it, you just think about it as a point. And even though, both of these are ways of representing the same pair of numbers, the main difference is that a vector, you could have started it at any point in space. It didn't have to start in the origin. So if we have that same guy but if he starts here and he still has a rightward component of 1 and an upward component of 3, we think of that as the same vector. And typically these are representing motion of some kind, whereas points are just representing like actual points in space. And the other big thing that you can do is you can add vectors together. So, if you had another, let's say you have another vector that has a large x component but a small negative y component, like this guy. And what that means is you can kind of add by imagining that that second vector started at the tip of the first one. And then however you get from the origin to the new tip there, that's going to be the resulting vector. So you might say this is the sum of those two vectors. And you can't really do that with points as much. In order to think about adding points, you end up thinking about them as vectors. And the same goes with 3 dimensions. For a given point, if you draw an arrow from the origin up to that point, this arrow would be represented with that same triplet of numbers, but you typically do it in a column. I call this a column vector. It's not 3, that's 5. And the difference between the point and the arrow is you can think of the arrow or the vector as starting anywhere in space. It doesn't really matter as long as it's got those same components for how far does it move parallel to the x, how far does it move parallel to the y-axis, and how far does it move parallel to the z-axis. So in the next video, I'll show how we use these 3 dimensions to start graphing multivariable functions.